So to start off, we have a graph. We have a load force and the length of a spring, and we'll apply our Oizerga. Origin. There is an origin there. The y-axis is force. The x-axis is length, so we should be thinking immediately of Hooke's law, F equals kx, and k is the force over the elongation, which has units of newtons per meter. So that's immediately we should be thinking of when we've got spring and forces and a load. The intercept in this case, the y-intercept, there is none, but the x-intercept says that when we are at about L1 over 3, the force equals 0. So not when we have a 0 length, it's when we have a particular length of about L1 over 3. We can read force and displacement. Gradient is delta F over delta X, which has units of newtons per meter. And of course, we remember this is the spring constant. Area is F times delta X, and that is Newton meters. And we remember that is the work done on the spring. So that's what we notice right off the bat. Which of the following gives the force per unit extension? So the force per meter, the newtons per meter. Well, the newtons per meter in this case is the slope when we have a y-intercept equal to 0. Because x is elongation, not the length of the spring. And so if we want to stretch the spring from L1 to L2, that requires a change in force of this much. So this is delta F, and this is delta L, and delta F is F2 minus F1, and delta L is L2 minus L1, which we see as this. This is a slope formula. We could divide F1 divided by L1 if it went through the origin, because in that case, then the second term in the equations will both be zeros. But that's what we need to look for there, is the slope in this particular graph.